We'll now take the newly defined concept of function using sets and combine it with something that we did a long time ago when we did logic, that is Boolean algebra. And we'll do this using Boolean functions. What is a Boolean function? It is a function whose whose domain is the set 0, 1 to the k, and whose target is 0, 1. So let's describe this. This is the domain, and 0, 1 to the k is the set 0, 1 cross 0, 1 k times, and this is nothing but strings, binary strings of length k. Binary strings are just 0, 1, 0, 1, 0, 1, like strings which have 0, 1 as their letters. And the target is simple. The target is just the set 0, 1. So it takes in a string of length k and either produces 0 or produces 1. Here's a very simple example. You can take the function f that produces 0 for every x. Totally valid function. You can have a function f that takes in 2 entries, so strings of length 2, and produces the sum. Here the sum is in Boolean algebra. So remember that Boolean algebra is like propositional logic, and the sum is like taking OR. F of 0, 0 is 0, f of 0, 1 is 1, f of 1, 0 is 1, and f of 1, 1 is also 1. And if I were to draw this using our previous notation, it would look something like 0, 0, 0, 1, 1, 0, 1, 1. The output is always 0 and 1, and 0, 0 is getting mapped to 0, and everything else is getting mapped to 1. Similarly, you can have the product function. Here I'm multiplying a and b, and this time I'll just draw a picture. This function looks slightly different. 3 of the things go to 0, and only 1, 1 goes to 1. And that's like saying only true and true is true, and true and false or false and false are both false. Okay, so we can describe functions, Boolean functions like this, but Boolean functions don't have to be describable in this way. I can just totally randomly create a function, something just like that. Let's still have 0, 0, 0, 1, 1, 0, 1, 1, 1, and I can just randomly assign things. So I can do something like this, like that, and this is a function. It takes in an input and produces an output. So this is a completely valid example. And as you can imagine, if I increase 2 to 3, then I'll have 8 inputs, and 8 inputs drawing it like this is not practical. So we do something like we did in logic, that is we build truth table. Instead here it's a Boolean table. And the same function, I can describe it as follows. So I'll say A and B are my 2 inputs, and FAB is my output, and I'll draw it as 0, 0, 0, 1, 1, 0, 1, 1. This should remind you very seriously of truth tables. And in the above example, 0, 0 is going to 1, 0, 1 is going, 0, 0 is going to 1, 0, 1 is going to 0, 1, 0 is going to 0, and 1, 1 is going to 1. So this is one more organized way of representing a Boolean function as a table. Notice it's like true, true, false, false, true, false, true, false. So it's literally a truth table. So a truth table is actually secretly encoding a Boolean function. Now we are going to do something very interesting. It turns out that even though I just created this function totally out of the blue, there is a way for me to describe FAB as a product or sum of things. Question. And the answer is yes. And there's a trick to do this. And the trick is this. You look at the table and you look at all the entries where there is one. So you have one here and you have one here. So I focus in on the first row. So here I want A equals 0, B equals 0 to give me 1. To go from 0 to 1, I can do the complement. So I'll take the complement of A and I'll take the complement of B and multiply them together. So that is the term I get by looking at this row. Now I can look at the fourth row. And here A equals 1 and B equals 1 should give me 1. And then the way I can do this is I don't need to complement either. I can just take A times B. Okay, so that's the second step. I'm not done yet. I'm just like, this is a process. This is a long algorithm. So for each row, complement the input 0 and multiply. Okay, so I've done this thing for the row number 1 and row number 4. And the final step is add the results of previous step. So in the above case, I will get f of AB is AB, A bar B bar plus AB. And this is my answer. Let me do one more complicated example to explain what's happening. And then I'll explain the theory behind this. So here is a bigger example. Here I have 3 inputs, x, y, z. So f is here a function that goes from 0, 1 to the 3 to 0, 1. And it produces something. And my question is again, describe f algebraically. And we'll do it systematically. So the first step is locating all the outputs which are 1. So all the outputs that are 1. Now focus on each row one at a time. And from this row, x equals to 0, y equals to 0, and z equals 1 is producing the output 1. So I'll complement x and y and leave z as it is, and then multiply them together. Okay, let me do the second on this side. So now x equals 1, y equals 0, and z equals 0 is giving me 1. So I will complement y and z, and I'll leave x as it is. And the reason I'm complementing y and z and not x is because these two are 0. Similarly, in the first case, I am doing this. Here I have x equals 1, y equals 0, z equals 1. So I only need to complement to the y. And so I'll get x, y bar, z. And finally, here I have all 3 are 1. So I don't need to complement anything. I'll just leave it as it is. Okay, so now I've got these 4 different terms. These 4 terms are, let me highlight them. Then all I have to do is add these 4 terms together. X bar, y bar, z plus x, y bar, z bar plus x The order in which I add these terms does not matter because you can always, a plus b is the same as b plus a. So all I have to do is just add them in some order, and that is my function. What is happening? So how is this process working? So the key is, let's focus on this term, the term x bar y bar z is 1 exactly when x is 0, y is 0, and z is 1. So only at this one particular input does this term become 1. Everything else is just 0. Similarly, for the second one, it is 1 exactly when x is 1, y is 0, z is 0, and so on. And so when you add all of these, you get the required function. I'll let you think about this. It's a complicated argument, but really it is about understanding how products, complements, and addition behaves for Boolean algebra.